In this work, we present a unified controller that enables humanoid robots to perform vision-driven reactive soccer skills in real-world environments. Without manual skill segmentation, the robot learns to search for the ball, chase it, and execute precise kicks, while adjusting its gait reactively in response to dynamic perceptual feedback. The robot is equipped with a camera mounted on its head for perception. To ensure rapid and robust response, we condition the policy on a compact state space derived from detection outputs rather than high-dimensional raw images. When ball tracking is lost, the robot actively initiates search behavior, maintaining continuous interaction and enabling long-duration play. In the final phase before kicking, the robot adjusts its foot placement in response to real-time detection. The control policy is trained in simulation using reinforcement learning and transfers directly to the real robot. We construct a soccer field environment in simulation, where the actor receives proprioception, goal location, and ball detections from a virtual perception module that mimics real-world visual characteristics. To integrate perception with control, the actor compresses historical observations through an encoder to fuse visual cues with motor state, and a decoder reconstructs privileged states from partial and noisy inputs. This design extends gain-based motion learning with perceptual grounding, where a discriminator provides style reward from human motion references. A multicritic framework is further introduced to decouple reward objectives and stabilize training. In contrast to rule-based strategies commonly used in RoboCup competitions, which require prolonged rotation and fine positional adjustments around the ball to achieve proper alignment, the learned policy seamlessly integrates approach and kick into a single coherent behavior, highlighting its agility in aligning with the target direction. The robot adopts an adaptive gait with shorter steps before kicking, allowing fine positional corrections to align precisely with the optimal contact point. The robot demonstrates highly dynamic and reactive behavior when responding to rolling balls. When the ball moves laterally across its front, it initiates swift lateral interception steps. When the ball rolls toward its rear, the robot performs an extremely rapid turning behavior. Even during temporary loss of visual contact as the ball leaves the camera's field of view, the robot actively rotates its head and torso toward the disappearing direction, successfully recovering visual contact to sustain tracking. When the ball is suddenly physically occluded, the robot continues chasing the ball and successfully completes the kick under short occlusions of approximately 0.3 second. For longer occlusions of around 0.6 second, the robot loses track of the ball after the occlusion and switches to rotational search behaviors before reacquiring the ball and attempting another kick. These reactive responses showcase the policy's ability to integrate visual feedback about ball movement into motor control, optimizing efficiency in dynamic tracking scenarios. To assess reliability of the controller, we measure kicking success rates across different regions of the soccer field, providing a comprehensive evaluation from perception to motor execution. The robot maintains consistently high performance in all tested positions, including backfield regions where even a 10-degree angular deviation can cause missed shots. The proposed controller was adopted by the Tsinghua Hephaestus team in both the RoboCup 2025 Adult-Size Humanoid League and the 2025 World Humanoid Robot Games. As the champion team, we further demonstrated its practical effectiveness in real-world competitive settings, where the robot operated under disturbances and visually cluttered environments, relying solely on onboard vision and computation. Despite these pressures, the policy maintained stable behavior during the matches and directly contributed to multiple scored goals. In interactive matches with human players, the robot even broke through the human goalkeeper's defense to score. These results highlight the capability of humanoid robots to perform reactive skills through tightly coupled visual perception and motion control in dynamic environments. By narrowing the gap between perception and action, this work takes a step toward human-level embodied intelligence, moving humanoid behavior closer to real-world application.